This is the second video on simulation. So let me change this to be as this is simulation one. It is actually simulation two. Let me get this as simulation two. In the simulation two, what is our intention is to find bubble point temperature and dew point temperature. In short, we can write this as BUBLT and DWT. Okay, so this is what our intention. Next, let us briefly understand what actually the each calculation implies. Bubble point pressure means bubble means liquid. We have liquid. First bubble of vapor forms. So that means we know the liquid phase composition and temperature specified. So we have to calculate pressure and vapor phase composition. That is our problem. Similarly, dew point pressure, dew means vapor. That means Y is given and temperature is given. What we are finding is this is known quantities, these are the unknown quantities. So that is what we have to understand. The left side is the unknown quantities, the right side are the known quantities. Bubble means that means X liquid phase compositions are known, and as per the requirement, which variable we are finding, pressure and temperature, between pressure and temperature, we have to specify the intensive variable. If it is bubble point temperature, that means bubble point temperature, that means first of all, if I say bubble, I know the liquid phase compositions. If I want to find temperature, that means I have to specify the pressure. So this is our problem. Similarly, if it is dew point calculation, so Yi is known and pressure is known. So this is known as dew T. So dew pressure. Now the problem here, you can see the problem which is specified here for the system methanol and methyl acetate. Now this is a binary system. Methanol is the component 1, methyl acetate is component 2. The methanol means OL is a alcohol, as we know. OL is alcohol and acetate is an ester. The following equations provide a reasonable correlation for the activity coefficients. Okay, these are, we don't have to worry. But what is intended here? A bit A, bit B, bit C, bit D. Now we are interested in bit C, that means problem C, which is known as bubble point temperature because X is known and pressure is specified. So that means we have to find Yi and T. Similarly, if you take D, Y is known and pressure is specified. That means we are finding temperature and Xi. So do. So this is what our intention is. As per the answers, it has the model which is used here is probably it is what is used here. So gamma is there. That means definitely modified Raoult's light is utilized in this particular condition. Okay. So when come to simulation, we need to judge properly what we have to use. So the bubble point temperature answer here, what is the answer is 331.2 Kelvin. And the dew point temperature and the dew point temperature, the answer is 326.7 Kelvin. Now you can understand dew point temperature is lesser than or greater than bubble point. That is what we have to understand. Bubble point temperature and dew point temperature. So these things will So let us see, let us calculate, and let us understand this concept now. Okay. See, this is also, this you have to be very careful here. Uh, in the first case, x1 is given as 0.85. It depends upon the mole fraction of the component. That means feed, that mixture composition also depends. If the composition is same, then we have to see the difference between the two. That means which is less, which is more. But here, the composition of the feed is also specified, mixture is specified. So we don't have to worry about which is less or which is more. Now, let us go to, okay, our what do you call, another screen of DW sim, which I've already kept open. Okay. Now this is the DW sim window. Now I open a new window here. Already I think one of the files is ready. So I say this is, again come back. I say new. Yeah. So I quickly go through how I am trying to specify. So this is the window. I press next. In the search bar, I press methanol, and I enter. Again, I take this in the search bar. Methyl acetate is the second component. Why it is not going? Yeah. So let me go to settings and compounds. Again, I press here methyl acetate. So it is, you can see methyl acetate here. So this is, again I've taken another compound and I say fine. Now I go to thermodynamics. Now we can choose the modified Raoult's law will not be provided here. It will be there Raoult's law or any other parameter. So modified Raoult's law, or we have to calculate what you call activity coefficients also. Let us choose a Wilson equation for suppose. Let us choose a Wilson equation now, and then let's see. Let's see what will happen. Now let me take this material stream and drag under the process flow sheet window. Let me actually make it bigger so that it is visible to you. Now this is a mixture. I click on this. Yeah. Now I am getting a material stream window. I take this as mixture. Press enter. Now I said this is Wilson. Now the stream conditions, compound amounts. Let's go to the compound amounts. In the C bit, you know, what are we trying to do? In the C bit, that means in the, we have seen that earlier, in the C bit, we want the methanol is 0.85. He has given in the problem to specify methanol to be as 0.85. That is liquid phase composition. If it is 0.85, of course, obviously the other component should be 0.15. Make the overall composition as 1. I accept it. Done. Now I go to stream conditions again. Now I have to calculate temperature. So I specify pressure and vapor fraction there and specify this vapor pressure as how much. What is the problem given? Pressure is given as 101.32, 101.33 kilopascals. So it is already shown as pascals. Let me change it to kilopascals. It is taking. So I say is 101.33. Press enter. Moles per hour. Let us change this as mole per hour. Okay, I am taking kilomoles per hour. Let it be kilomoles per hour. I name it as 1 kilomole per hour. Just taken moles per second. Let me take kilomole per hour. Yeah. So it has converted. Or I go to settings. I go to system of units. I gather this as C file, wherein I can change this bar kilopascals. and mole flow rate is kilomole per hour, which is by default. So now again I come back. Now check what has happened. Now, if I want to calculate bubble point temperature, I make this vapor phase mole fraction to be as, let me actually show you this way. Yeah, this partial portion. Vapor phase mole fraction to be as 0. Next. Yeah. Now again, come back here and then let us see. Now, what have we chosen? So this is where we have chosen flash spec is pressure and vapor fraction PVF. So this is what our intention is. In that I specified this pressure and I've given vapor fraction. Now I got the result as 58.182. So this is my result. So what is the answer I got? So this is bubble point temperature. That means what should I specify? P and X. Okay. So P is 101.33 kilopascals and X is 0.85. Instead, I can even say this is X1. So what should I calculate? Temperature. So temperature is how much now? 58.1828. So this is the, what you call, bubble point temperature. Now with the same composition, if I want to calculate the dew point, what you call, temperature, I am saying same composition, dew point temperature. What should I specify now? I want the pressure and I want Yi. Again, pressure is same, but Yi now I say the given composition which is given as 0.85. I choose this as vapor phase now. I calculate again temperature. Let me now. So what should I do now? I have to change the vapor fraction to be as 1 instead of 0. It should be 1. Now I press enter. Now I see again change. What is the bubble point, dew point temperature now? 60. Oh, this is 61.73. So now you can understand the temperature, bubble point temperature is less than dew point temperature provided at the same composition. Once I assume the feed mixture composition to be as, or mixture composition to be as liquid phase, and I find an estimate temperature, that is number one. Likewise, I calculate the other things. So to summarize what we have learned today, we have known what are the different calculations and how do we calculate bubble point temperature and dew point temperature using in the simulation engine. So this can be validated with others also. So what is my answer here? 58 degrees centigrade, right? This is centigrade. So with the centigrade, how much will be the, what you call, in Kelvin? So 273 add, so 3 plus 8 1, 5 plus 7 2 3 and 3. So 331 Kelvin. So what is the answer we have obtained? What you call, as per the textbook? The answer what we have obtained as per the textbook is fine, right? It is 331 Kelvin. Exactly, it is matching the, what you call, the calculation what we have done with modified Raoult's law. Okay. Okay. We'll see you in the next video with yet another beautiful learning.